Okay, so I don't have the homeworks graded, but I do have your test graded. I was gonna wait and go through that on Thursday. Okay, so if you wanna see what you got, you can come in and talk to me. I still might actually give you a problem, say do it, need some extra points. Some of the multiple choice was kind of scattered, like maybe 3 people missed one question and then 3 people missed the other one, but that's like 20 points. And I'm like, okay, that's not quite the way I wanted it to go. So overall, I think you understand the concept. I think you just missed one little aspect of it. So I was actually happy with the test. I was happy with kind of the outcome of where people were. It's just, if they would have just answered this one question right, they would have had 20 more points, you know what I mean? So I don't think that's quite fair, so. I don't know, when I was grading them, I was very surprised, not surprised, but like, okay, you're actually, you kind of know what you're doing, so that's good. So the plan right now is to kind of continue what we're doing, but kind of more of, you remember the fan problem on the last homework? We're going to look at angular momentum. And so we're going to do this problem. We'll do as many problems as we can today and next class. And then we might have probably a work day, but it might be, I cover one little concept first and then a work day. And then I'll probably have another test. But that's a few weeks away. So. But right now, for today and for Thursday, we're going to cover this stuff. Okay, I'll post. I don't know if I posted the new homework, but I will. It deals with stuff like this and another problem that I'm going to give you that we'll go through. Okay, but I probably will have a work day. Let's see, next Thursday. We'll probably come in here first. Here. Okay. Everyone else got one but you? Huh? Oh yeah, you need one. I thought there was one more. Now if this keeps acting up, I don't know why it's doing this. Okay. All right, so let's go ahead and let's do this problem. So we'll spend today and Thursday working on this stuff. Come in after break. We'll have one day next week, right? Which is Thursday. Come in here. I'll go through one last easy concept, and the rest of that time will be a work day. Okay. So let's go ahead and do this. So we have. What is it? What does it say? Just grain? Yeah, okay. Yeah. So grain falls straight down, hits this conveyor belt, goes down this conveyor belt, and spits out at the end. Okay? And what we're trying to find is, what are we looking for here? Determine the reaction forces. Okay? So what I'm going to do is we'll set the problem up, and then we can go through numbers if you want. But really, the biggest thing I gave this as a test a couple years ago, is how do you set this problem up? All right. So let's go ahead and do a sketch. I'm going to start right at C, kind of curve down. So we're doing a control volume. So I guess if you want, you can just kind of do a dotted line. But we're really kind of doing a free body diagram on this shape. Yep.
Oh, excuse the bridge is dumb.
Maybe his plane right out of fuel.
Yeah.
Okay, so at point C, what type of forces do we have? Wrong.
Pinned. Yeah.
It's a pinned, so we have what? A B. Roller at B. It's hinged at C, right? Does it say that?
Yeah.
Yeah, hinged at C. So we should have
and
I was waiting for someone. So CX and,
C1.
oh, hey, I didn't know I could do that. So CX, CY. Oh. Sorry, Devin, I didn't mean that. I just was hoping someone would say that and be like, yeah, I got him. But that's good that you spoke up. But at B, there's only what? Just the vertical one. I'm going to call this FB. Or you want to call it CB. Doesn't matter. I don't think it matters. So we have the reaction forces at C. We have the reaction force at B. Might as well put the weight force in here, right? And that X here. And that's W. Then might as well label here. This is in. And then we have something coming out. And what I'm going to do is I'm going to split it up into two components. So we have, oh, I don't want to do it that same color. Why didn't it switch? Here. And, oh no, we can leave that. We'll just do it at that angle. Was it 10 degrees?
Yeah.
And we'll just label that out. Because sometimes it gets kind of cluttered. So 2. All right. So we labeled the forces on the left side of the equation, and then we labeled what's coming in and going out. All right. Here you go, dude. All right. So our basic equation, start with out minus in, right? And we know where there's two directions. So we'll do X direction. And we'll zoom out just a tad. Is that okay? So I think all we have is CX, right? And let's make those directions positive. So X and Y. So CX. And actually this whole term goes away, right? Because control volume isn't moving. What's coming out in the X? Well,
FBX. FBN.
Oh, you mean this right here?
Yeah.
Yeah, I'm just going to call it M dot 2 V2X. Is that okay? So this is a velocity coming out, and we're going to do the component of it, which I think is, I didn't do these numbers, but that's fine. It would be cosine. And the velocity is going to the right, which is positive, so our sign convention is correct. So let's do the y direction. We have a lot of these forces, right? We have CY, we have plus FB, we have minus W, and we'll set that equal to
So we're
something.
not neglecting it.
Nope, not in this one. Nope. Knowing that the combined weight of the chute and the grain. Yep. Yep. So we have to combine it. 600 pounds. Yep. So we got all the forces. Now what's coming out in the Y? We have m dot 2 times what? A negative V2Y. So this is coming out of our control volume. This brown vector, I can actually, why don't we do that right here? And so this is V2X, and that's V2Y. And I put the negative because it's downward, with our coordinate system is up. Anything else going out? No. Then we have subtract m dot 1 times what? A negative V1. And we already know that's in the Y direction. Because that's straight down.
Well, we have to use sine for V2Y.
Yep. So I'll write that down next line. And let me put the negative in front here. Negative m dot 2 V2 sine theta plus m dot 1 V1. So again, always remember that keep an eye on your sign conventions for your velocity because they're vectored. The mass flow rates are just rho AV. Okay, there's no component in that velocity for that velocity. It's just the amount of mass coming out of that section in that control volume in that direction. So, basically, this is a good review of what we just covered. Okay, hopefully it even makes more sense now. All right, actually looking at the test I was telling everyone earlier, I was pretty happy with the outcome of it. So there is some of the multiple choice that probably were worth more than I probably wanted to. So I'm going to probably give you a problem, say, do this problem, get some extra points. Okay, but this is a good review. So we're stuck here, and we're looking for CX and for CY. But we don't know what. Let's go over here to the red equation.
We don't know C.
We don't know. Well, could we find CX?
Well, yeah.
We could find CX. Okay, so that's doable. But over here, could we find CY? Do we know FB? No. So then we're stuck. Okay? So what do we need to do? What have you done in statics? Moments. Where are we going to do a moment at?
B. At 2 because 2
Well, if you do it, okay, this is
Well,
good. So if you do it at,
You can't do it. I'll find it.
exactly, yeah. So don't do it at B because that's what you're looking for. You want to do it at A. So we're going to sum the moments at A. Or is it C? Oh, C, yeah, sorry, C, yep. That's stupid. They should have had an A, B, C.
Well, they go to G.
Or they go to G, don't ask me. So this is the equation that you should have used on the last homework set, which I need to look at. And we're going to find the moment at C, right? Okay, C.
You looked at the equation before you.
Sorry. Which way do you want, actually I'm going to pick because I did it this way. We're going to assume this way is positive. Just throw some stuff. So again, if you noticed, I don't put on our free body diagram, I only put the external or the forces that need to go on the left side of this equation. Same in here. So what's your first moment? SC. That's on the right side of the equation. So that's so the weight force. The weight force. Yeah. So that's going all the way around this way. So it's a positive moment, right? So we have W, and what's the distance? 7 feet. Yep. Those, yes. Yep. Next one.
Moment at A.
Well, that's on the right side.
Right.
That's the. We just. I think, you yelled at him for doing it.
Yeah. Well,
Then you slapped him for yelling back at
I
you.
wanted to imply that he was stupid.
No. So what's the next force? Yeah, minus FB, thank you, times 12 feet, yep. Okay, so now, if you look here, we got to do, what do I have? It should be out, so I have m dot 2 times v2y times what? Does everyone see that? I had to split out this component because it's shooting upward or downward, right? But what's that distance from point B to 12, right? Does everyone see that one? Because, I'll draw it over here, this velocity, I'll make it nice and yellow, how about that? So this has this component, and then this one is down, right? So, yep, that would be 12, and then what would that distance be for X? 6 feet, yep. And that is a negative or a positive? The Y, this moment would be positive. The other one should be, yeah, because we don't never go that way, so that one's going to be negative. Yep. Yep. So that's times 12, and then we have a minus. Oh, you don't want yellow. A V2x times 6, and then we subtract what's coming in for the moment,
Well,
which
can we
is
just put brackets around the first or
Yeah.
second, please?
we can do that certainly, and I'll put this minus as in blue. Yep. And then this should be m dot 1 times v1 times 3 feet. Are we correct on that one? And that's a positive moment, but it's, remember, the equations always subtract in. So that's cool, right? And we can use this moment equation to solve for FB. And it's very similar. Yep. Okay. I'm not gonna. I can give you. I don't even know if I have the answers. Let me go back, and I can give you the answers and finish this. But this is really the biggest thing, is knowing how to set this problem up. Okay. So
600 times 7.
So let's just recap this. So over here we have grain falling into our conveyor belt, going out, and then it shoots out at 10 degrees. What we did is we did a control volume on the grain, We labeled all our forces acting on our control line. Okay, so we have the reactions at C, we have the reaction at B, we have the weight, and then I labeled our velocities coming in and going out, which is 1 and 2. All right. This out has two components, X and a Y. All right. So when we did the X direction, we only had CX, which is our reaction force on the left. And then the right side, we had only going out. So we had m dot 2 times v2x. We split that velocity into a component. Okay? So we ended up getting v2 cosine theta. Then, in the y direction, we have three forces on the left. Remember, those forces that you draw on your free body diagram could be pressure, weight, or reaction forces. Okay? I didn't do any pressure forces. How come?
Because they're all capable. Because it's all open.
It's all open to the atmosphere. So pressure acts on the top and on the bottom, and it all cancels each other out. Okay? All right, do you guys remember when you did the hydrostatic forces in fluids? You never had to worry about atmospheric pressure because it acts on both sides of the dam and they cancel. So there's no sense of really putting it on the diagram because it's just all going to go away. Okay? So again, you could have pressure forces, you could have reaction forces, and weight forces, which are called body forces. Okay? Then on the right side, in the y direction, we have one going out, but this velocity vector is negative because it goes downward. And then we subtract what's coming in. And again, this velocity vector is negative. That's why we have negative. So we end up with a positive here. We have the negative here. And then we find out that we can solve for Cx. However, we can't solve for Cy because we still don't know Fb. And what we need to do is do the moment at point C and actually solve for your Fb. All right. So this is angular momentum for fluid flow. Okay. The very first problem in your homework, actually I can show you. It is recording. Good. Just gonna give you an idea what the homework's looking. Angular momentum. Wow, we're only in homework 5. I don't think it is. I need to fix that. Yeah. Yeah, week 5, yeah. So there's 3 questions.
Have we done something very similar to that?
This one?
Yeah, this one seems familiar.
No, but you probably did one kind of similar, probably last homework. Yep. So this one, you have a hydrant, water comes in the Y and shoots out in the X, but over here shoots out X and Y. And I believe it wants to find,
I've never seen fire hydrant.
no? I don't know.
It's gotta be European.
Determine the horizontal and vertical reaction forces, okay, which occur down here, Cx, Cy, and the moment generated down there. Okay, so that's question 1, which is you're going to do the angular momentum. Yep, you might have to do some of the forces too. Yep. So that's problem 1. Okay. Problem 2 we're going to go through here next. I think this last one is MATLAB, but I'm going to probably give you a couple days to work on stuff. Well, she's trying to slide.
Backwards?
Yeah. So what's usually skates on ice, we can assume frictionless. So when she turns this on, she moves at a constant speed. That way. Okay. Constant speed means no acceleration.
Come on, Will.
Okay.
But
There's no
friction. Yes, but initially yes, but we'll assume after that, don't worry about it. But I'm going to go through a problem like this with satellites, and I'll give you one. Okay, one example, and you apply it the same way. This one's actually pretty short. compared to number 1. Okay? Then I don't know if we might start one of these problems, but you're going to get pretty much, we're going to do one exactly like this, but maybe with slightly different numbers, so you have it all done. I just want you to change some numbers, I believe, and then plot it. Okay? But when we get to this one, you can. So this is a sprinkler. Water comes in, out of the page, shoots out, and you want to figure out what the length of each sprinkler. No, I want you to find the RPMs, and I think that's all we're doing. Yeah, trying to figure out how much water you put in, how fast is this going to spin, and depending on what these angles would be. Okay. Yeah. So I haven't updated it yet, but these are going to be your 3 questions. Of last year, Will. So you're late. Okay. Let's go through.
Time yet again, Will. Oh man, you're on top of it.
You have to go back in time. Okay, so let's do this one. Now the printer printed it on back both sides because I asked for 12 copies and it printed 6. I print 12 more.
Yeah, why does it do that?
I don't know. You can't change it. Delete it. So we waste more paper. Think about it. Well, ink, I guess. Not the same as paper.
By trying to force the conservation of paper.
What's the matter? All right, let me get this up. Week 6. Nope, wrong one. Go to this one. Week 6. Day 2.
Oh, it's like around scale chapel. You're right. You're so bad.
Okay, so we have an orbiting satellite, has a mass of 3,400 kilograms and is traveling at a constant velocity. To alter its orbit, attached rocket discharges 100 kilograms of gases from reaction of a solid fuel at a speed of 3,000 meters per second relative to the satellite in the direction opposite of the Earth. The fuel discharge rate is constant for 3 seconds. Determine the thrust, the acceleration, and the change of velocity. Okay. What's that? Yeah, I mean, and then actually it's not too difficult to analyze. So here, let's start right with the force equation that we have. Yes. So we can't, well, let's go on the left side first. We're in outer space. Now,
There's no gravity.
we're assuming that our laws and people guesses are right and there's an outer space. There's no reaction forces. There's no forces at all in outer space. Okay? So this whole term on the left is 0. Yeah. Yeah, you have 0 vacuum acts everywhere. Sure. Okay. There's no friction forces. There's no pressure forces. There's nothing. Okay.
There's no gravity. The world's flat.
Yeah. Well, we're not even worry about that. We got to leave this term in because it's accelerating. And is there any fluid coming into it? No.
No.
And there should be only probably one going out, right?
Yeah,
So which way is this satellite moving?
it's the right.
To the right. So we have plus m dot out times what? Positive or negative?
Negative.
Negative, yes.
I hear that.
Because the satellite's going to the right, and this gas is going to the left. So that's a vector, so it has to be this sign change. Okay, so if I bring the MA term over, and I keep this like this, oops. The thrust that's generated is just your mass flow rate times velocity. That's what thrust is actually defined as. So anytime you have a rocket
So
or
you're considering MA as
or I would say yes, it is in this case,
thrust, right?
but really mass flow rate times velocity is thrust.
Okay.
So if you have a rocket and it's shooting straight up, if you know your mass flow rate of the gases being expelled and the velocity, that's the amount of thrust. Okay? So that's what we're looking for. I gave you the velocity, right? Yep. So we need to find m dot. How do we find m dot? So the fuel discharge rate is constant for 3 seconds. How many kilograms in 3 seconds? This is to alter a test rocket discharges 100 kilograms. So this thrust would be 100 kilograms over 3 seconds times 3,000 meters per second. And we get a thrust of 100 kilonewtons. Isn't that crazy?
That's our answer to A.
That's the answer for thrust. Yep. So, because you know mass flow rate is mass per second, right? Yeah, in 3 seconds. Yep. So 100 kilonewtons of thrust. That is a lot. But it's shooting out at 3,000 meters per second. I don't even know what that is in miles per hour. I don't know. That's pretty fast. 2 million? Wrong. Come on, Will. Your turn. Your plane doesn't go that fast?
That would be 6,710.81 miles per hour.
Oh, that is pretty fast. All right. So how do we find acceleration now? Yeah, we just substituted MA for M dot V, right? So we're just going to say the thrust equals MA, so A equals the thrust over the mass. And what is the mass?
3,400.
Yep. So technically, what's that? Yeah. Yeah. Well, I substituted this to that. So in order to find the acceleration, you already know the m dot v, and you just set that equal to ma. Yep.
Did you get
So the 100 kilograms,
100
we're going to assume is kind of neglected, but also it depletes. So say all the gas is
Okay.
gone to that 100, and then, okay, go ahead and use it. Yep.
29.4?
Yep. Yeah, 29.4, yep. Technically, if you wanted to find the acceleration when it first started to the time, you'd have to kind of chop these up, right? Because initially the mass is 3,500, and then the whatever, okay? But don't worry about that. Just worry about it after. So we get 29.4 meters per second squared. Yep. All right. So we now know how fast this satellite's accelerating. How do we now find velocity?
Well, what's the velocity from
Not the derivative. Huh? You can multiply by time. Yep. Or if you remember from physics, A is dv dt.
Yeah, I don't think you know that.
But A is a constant, so you already know that V equals V naught plus AT from physics.
And B naught.
And this is why it's 0. That's why it's just times by T. Yep. So this would become 29.4 meters per second squared times 3 seconds. We get 88.2 meters per second. Say that again? Yep, a little dynamics. Yep, a little bit of physics. So if this satellite was in space and we somehow were holding it there, we would need 100 kilonewtons of force to hold it. Okay? So just to give you an idea, to hold it in place while it's discharging. Yep. Isn't that crazy? So this, you do this very similar to problem 2. Because problem 2, the girl's skating. You assume that it's frictionless. There's no other forces acting in the X direction. Go ahead and solve this. Okay? So this is problems when you don't have any external forces. Okay? All right. Why don't we take a 5-minute break, and then we'll start the sprinkler problem. We're doing pretty good on time. So, okay, so I'm going to pause this. Okay, where are we here? All right, so water enters vertically and steadily at a rate of 10 liters per second into the sprinkler. Both water jets have a diameter of 1.2 centimeters. Disregarding any frictional effects, determine the rotational speed of the sprinkler and the torque needed to prevent the sprinkler. Okay? All right. Given V dot 10 liters per second. The diameters 1.2 centimeters. R1 is equal to R2, which we'll call 40 centimeters. Angle 60 degrees, and density of water will do as 1,000 kilograms per meter cubed. And here's my sketch. Put that right there. Move that up. Label it sketch. And draw control volume, and it's going to be a circle. Oh, why is it got to be yellow? No, but it was yellow. Or was it yellow?
You can't turn it yellow.
I probably could. I just haven't tried it. So it's spinning this way, and we have a torque T that way. And we have, we'll call this 1 coming out, and over here on the right we'll call 2, and this we'll call theta 2, and this is theta 1. They're both the same. What are we looking for? We're finding omega and a torque. And let's write some assumptions. It's discharged to the atmosphere, so we'll neglect, well, I mean, we'll just, those are 0, so just discharge to atmosphere. Okay, and again, so the pressure all the way around this control volume is all the same, so they all go away. At steady state, so the 10 liters per second is always coming in at 10 liters per second. And we're going to neglect drag forces and friction forces. Okay, so that's what I'm doing here. So far, okay? All right, so let's, what do I do here? Let's look at location 1. So I'm going to make a new sketch. Let's do the solution. And I'm going to make a new sketch. So this is at location 1 where the water shoots out. It shoots out. So this is V1. Make a new vector here in purple. Okay, so this is V1 cosine theta. Then I'm going to do another vector down this way, and this is the velocity of the actual sprinkler, or the nozzle. So what we're going to do is over here we're going to find V1. So over here on the left, V1 is velocity shooting out, so the water shooting out of the sprinkler. This is just a component of it. All right, I took that because we're going to look at this direction. And this N, Vn, is the velocity of how the sprinkler is moving, because the sprinkler is spinning this way, but the gases are shooting out that way. Okay? So what we need to start with is conservation of mass. So the amount of flow coming in is split into 2, right? Technically, this is 2V dot out, because they're the same. The volumetric flow rates going out, I just combine them, so there's 2 of those. So V dot out is equal to V dot in divided by 2. So let's just plug those in. So we have 10 liters per second times 1 meter cubed. There's 1,000 liters. We divide that by 2. Get 0. Whoa, 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 whoa. You get to 0.005 meters cubed per second. All right, now we can find V1. V1 is A1, whoops. V dot 1 is A1 V1. So V1 equals V dot 1 over A1. So 0.005 meters cubed per second divided by pi over 4 times 0.012 meters squared. The whole thing squared. Thank you. Yep. Yep. So that's the diameter, right? Yep. Okay. So far, makes sense. Everyone's following along? Yeah. So now what we need to understand is this velocity. Let me write this so we have it. Is a relative velocity. Okay? So this velocity of the jet respect of the jet with respect to the nozzle. Okay? So just got to remember that. It's not what the person would see standing away. If you're on the nozzle, this is what you would see shooting out. Okay? Just know that. So this is written kind of like velocity of the jet with respect to the nozzle, and we're going to call that V1. Okay? So do you remember, actually, do I want to go, yeah, minus, that doesn't matter, I'm going to keep going down anyway. Do you remember the velocity, relative velocity equation? Some of you should. It's the what minus the bottom. It's the velocity of the jet minus the velocity of the nozzle. And these are actually vectors, right? Oops. This is a J, sorry. Oh, still messed it up. Velocity of the jet with respect to the nozzle. There. So, just as a reference again with relative, if we're standing on the nozzle and it's spinning around, we would see that velocity v1. Okay. However, if you're on the side looking at the sprinkler, and the sprinkler is going to the right, okay, and you have stuff shooting out that way, it actually looks like it's going to go faster, right? Because it's addition here. Okay? All right, it looks like it's going wicked fast because they're going opposite. Okay? Just like if say we're driving down the road and I'm going 60 and someone passes me going 65, the difference would be 5. Okay? But if they're coming at you and you're going this way, it actually looks like it's coming quicker. Okay? So just always remember this. When they're given these problems, we need to figure out the actual velocity from an observer and a fixed reference frame. Okay? All right, so we always need to figure out what this jet velocity is to use in our force equation. Okay, so I'm going to write this down. Just always remember that. That's the biggest thing that we have to worry about. Okay, because there's relative velocities going on here. So, in our case, we have, let's go back up to sketch here. We have this direction. Okay? We're going to assume up is positive. And so now the velocity of the jet, which is what we're going to actually use in our equations, is v1 cosine theta, okay, which is the velocity of the jet with respect to the nozzle that I just showed you. And then plus Vn. Does anybody know if something's rotating around, how they find this component of velocity? Something's spinning with an angular velocity. And actually Vn, this actually, because it's vector, you want to write subtract, right? Because what direction is Vn going? Down, yep. Omega r, have you heard that before? Which is your tangential velocity at the end of there. Yep. So that's where the omega comes in now. Okay. So this nozzle is spinning around with an angular velocity called omega, or you can convert that to RPMs really. If we multiply that by the distance away, that gives you your tangential velocity component. So this is the velocity that we actually need to use in our sum of the forces, or some of the moments that we'll talk about here in a second. Okay?
Do we need to find WT to find WR?
You need to find what?
WT.
WT? What's
Yeah,
WT?
it's like tangential force. So I thought that WR is like, the equation for that is WT cosine theta. Or is that not what it is for this graph? No.
No, not sure.
That's just what it is for the machine doing. I know those are the same.
For the force? No, we're just only converting this velocity. So always remember that if you know the angular velocity, which you can find by RPMs, if you multiply that by your radius, you know your velocity actually at any point you change your radius. Okay? That's all we're doing here. Yep. All right, so let's start with the angular momentum equation. Which states the sum of the moments equals sum of the moments of your fluids times your radius. So I wrote it slightly different, but it doesn't matter. And again, this velocity is Vj. That is your velocity relative to the ground. It's from a fixed reference point. That's what you always have to remember. And actually this time I picked counterclockwise as positive. So on the left, we have a torque, which is a moment. We'll just call it T. So we're doing it right at the center of the sprinkler. Okay? So there's a torque that's generated, which is a moment. Then on the right, we don't have anything coming in, right? That term goes away. And how many terms are we going to have going out? 2. Yep. Okay. And let's make sure I have this. So let's write it and check. So minus R1 M dot 1 times VJ1 minus R2 M dot 2 VJ2. All right, so let's just scroll up and look. So let's look at this one. So we have this shooting out that way creates a negative torque. And if you flip it on this side, the water shoots out this way, right? And it goes that way with a negative torque. So let me just flip the signs. Okay, R1 is equal to R2, right? So we'll call that R. M dot 1 equals M dot 2, which is what? M dot N divided by 2 from conservation of mass that we already did with volumetric flow, right? And Vj1 equals Vj2. And we'll call that just Vj. So we end up getting the torque equals R V times J M dot there'd be 2 of those, right? So they would cancel. So M dot N. I was like, where did the 2 go? Because, let me show you. Based on this, if we factor out, we'd have M dot N over 2 for M dot 1, and M dot 2 equals M dot N over 2. And you combine these two because they're the same, you have 2 over 2. All right. And why don't we just plug in R M dot N, and this Vj was what? V1 cosine theta minus R omega. So that is the torque equation for the sprinkler in terms of failure. So what I would do for problem 3 is redo this, make sure you understand it, and really this is what you're going to plot. Okay, but two things that we need to finish. Be nice to finish it and then Thursday. No, it should have been negative. Yes. Yeah. Okay. Yeah. So come in here Thursday. I'll go through the test. We'll review this stuff. Maybe I'll finish this then. I'll stop here then. That's good. Now I can review. Should have been minus because VN is opposite our positive direction. Yep. Yep. All right. So let's just stop here. I'll finish this. I'll show you what happens when it's free spin to find omega and what the torque would be if it wasn't spinning. Okay. All right.